It is perhaps the biggest mystery of all. What happened in the Big Bang over 13 billion years ago? Here on the French-Swiss border, experts hope to find some answers. The project is based in a giant circular tunnel 100 metres underground. Particles are fired round it in both directions at close to the speed of light. The collisions recreating the conditions moments after the birth of the universe. It's one of the biggest scientific experiments the world has ever seen. And it all begins right here with a simple bottle of hydrogen gas. This is a replica. The real one is inside this high security cage. A lot of the equipment here is at a very high voltage. Now inside, the gas molecules are broken apart to produce a beam of tiny particles called protons. 100 million protons a second are sent whizzing down this pipe into an accelerator and off into the Large Hadron Collider. The huge collider has taken years to build and cost billions, but it could discover strange new particles and even new dimensions, revolutionising our understanding of the cosmos.
But this machine, we know, will open a door to a deeper understanding. We don't know what's going to be through the door, but we know it will do that. So it's incredibly exciting.
But the powerful particle collisions could create black holes. So is there a danger they'll destroy the planet? I asked one of the world's most famous scientists what he thought.
Collisions at decent greater energies occur millions of times a day in the Earth's atmosphere, and nothing terrible happens. The world will not come to an end when the LHC turns on.
And the discoveries to come should provide new insights into our world. Christine McGurty, BBC News, Geneva.
And we'll be speaking live to Christine a little later in the programme in Geneva. And also we'll have live coverage of the start-up of this big event at about 2.5 hours' time, right here on BBC World News. And, of course, you can follow it on our website, bbc.com. Stay with us for all that.
And one of the amazing things about it is the sheer volume of data that we're going to get out of it. And in fact, some of these computers in the control room here are connected up to this fantastic thing called the grid, a computer to communicate all over the world so that a lot of people can get involved in analysing the data. Tell me a little bit about that.
Well, the amount of data that is being processed by these big detectors that we're building is about the same as the whole world's telecom network. So it's an immense amount to just try to process. And you can't do that even with a few supercomputers based on site. So we try to distribute this effort all around the world. And this is where the grid comes in. Now, some people think it's like the next generation of the World Wide Web, which again was invented here. So what we're trying to do is spread the word, spread all the data out, and get everybody around the world involved in this, whether they're in Uzbekistan, whether they're in the UK, whether they're in China, the US, anywhere. And as you see from the people around, they're from all nationalities. On this experiment alone, we've got about 40 different nationalities involved. So it's quite different from most people's experiences, really.
And there could be spin-offs. I mean, it's amazing, cutting-edge research, new insights into the universe. We can talk a little bit more about that. But we're just going to listen into the control room because I think something's going to happen around now.
Excellent.
Okay. 5, 4, 3, 2, 1, 0. Nothing. Yes, sir. Yes. And here. Voila.
Joining me in the studio is Marcus Chown, who's a cosmology consultant for The New Scientist, also an author of books on all sorts of subjects aimed at trying to help us to understand. The latest, Quantum Theory Cannot Hurt You. Well, no, nor can we understand it, and that's half the problem, Marcus. They're very excited, clearly, but what is this about?
Well, basically it's about figuring out the origin of the universe. I mean, when they talk about recreating the conditions that existed, in the first split second of the universe in the Big Bang, they're talking about understanding the laws that actually brought the universe into being. The laws that ended up creating the stars and the galaxies and you and me and the world that we live in. So really, it's ultimately about origins, and we're all interested in origins. Where did the human race come from? Where did the Earth come from? Where did the universe come from? Why are we here?
Now, I know we're not going to get a simple answer to that, and certainly not today, but do you see this as a groundbreaking historical moment?
I do, actually. I mean, this is the last in a series of experiments which began in 1909 with Ernest Rutherford, Lord Rutherford, who actually smashed into the atom and discovered the atomic nucleus at the centre of an atom. And these experiments have got bigger and bigger and bigger, and this is the last, it's the era of Rutherford's experiment. And, it will probe deeper into the inner structure of matter and teach us more about the ultimate laws which actually orchestrate our universe.
I suppose what's so difficult is we hear about, the Standard Model and how incomplete that is. At Higgs boson I've been presented with here, I don't understand those things. Translating anything that happens in CERN into a language and even a concept that we can grasp is perhaps an even bigger challenge than getting the answer to the question.
Absolutely right. I mean, for the last at least 100 years, we've discovered that ultimately, beneath the skin of reality, nature is very, very counterintuitive. It's not like the everyday world. It is stranger than science fiction. An atom can literally be in two places at once, the equivalent of you being in London and New York at the same time. Now, how do you get your head around that? Now, why the universe at its deepest level is so strange and so different from the everyday world, we don't know. But as you say, as a communicator, it makes it very, very hard to convey what's actually happening. You mentioned the Higgs boson.
Don't go too far on it.
One of the things that we really don't understand is the origin of mass. I mean, you would think by now we would know why you weigh 75 kilograms or whatever. Why it's difficult to push you. Why we don't know that. It turns out that these theories that we have, which describe the four fundamental forces of nature, can only show that they're all facets of the same force. They can only do this by assuming that all the particles, the building blocks of you and me, are massless. So there has to be some other mechanism to give particles mass. A guy called Peter Higgs in Edinburgh in the 1960s came up with this idea called the Higgs mechanism. He said that the whole of empty space was full of these kind of Higgs particles, and when anything like an atom moves through empty space, it accumulates these things around them, and they give it mass. So they're looking for that.
Wonder if they'll find it. Obviously, a long way to go yet. Marcus, for now, thank you very much indeed for bringing a little bit of light into a very dark subject for many of us. Right, what has become of North Korea's leader Kim Jong-il? And there he was, gone. We are at least sucked into the excitement. With me in the studio is Dr. Simon Singh, a science writer and former particle physicist. Simon, thanks for joining us. We're learning a bit about what they're trying to do and how they're going to do it. Why is it so important to you, for example?
It's important to me because I'm human, and part of being human is being curious about the universe around us. For thousands of years, the ancient Greeks looked up into space. Every civilization's wondered what the universe really is, what it means, and the experiment that we've seen just start today, it's only the start, will begin to answer those absolutely fundamental questions.
But I mean, one scientist called this, we're seeking the theory of everything. Is it that big?
Yeah, a theory of everything encompasses what matter is and what the forces are between them. And bit by bit, we pieced it together. We understand what gravity is, we understand what magnetism is, we understand what the electric force is. But putting it all together into one simple theory that fits together is the ultimate goal. Over the centuries, physics has shown that the world is stranger than it seems, but also in a way simpler than it seems. And we're inching towards that bit by bit.
Well, I've been learning some things in the course of today, thanks to this, that I never understood. I probably never will entirely. But I suppose one of the challenges, if you get those answers, how do you ever explain them and make them pertinent to the likes of me, to the likes of the vast majority of us?
Well, I think all of these things can be explained at different levels to different people in different aspects. But, for example, one of the things that has emerged out of the physics of CERN and laboratories like that is the fact that the elements that you and I are made of, the carbon, the calcium in our bones, the iron in our blood, wasn't created in the Big Bang. The Big Bang furnace couldn't create those elements. And the way they were created was in the stars. As the stars collapsed, they would have created the heavier elements, they'd have thrown these elements out into space, they'd have formed new stars, new planets, and we emerge out of the remnants of those solar explosions. So one way to look at that is that you and I are just stardust. Alternatively, we're just nuclear waste.
Right, let me bring you back to Earth for a moment. $10 billion we're told this has cost. How do you justify that as money well spent?